Hello, everyone. So, we've been discussing a little bit about how data can be structured for the purpose of materials informatics, and we looked at data repositories, and we also looked briefly into the process by which materials are discovered. So, as we go forward, I would like to start with what I think is one of the early attempts at really doing data driven material science. And so that's where we come into this concept of structure maps. So, the structure maps, the idea behind the structure maps is fairly simple. The goal was that you want to use simple elemental features to predict the crystal structure of binary compounds. Now, predicting the structure of binary compounds is actually a fairly challenging task because there's a lot of play that you have as far as the chemistry is concerned. There's a fairly large size palette when it comes to looking at the periodic table, where you've got a good number of elements. And so it is really a fairly complex task to predict the structure of binary compound. What made it even more incredible is that this is an effort which took place sometimes in starting in the early 1980s. And so the two pioneers in this field were Pierre Villars and David Petitfort. So the initial attempt at making structure maps was done by Villars, and then after Villars published his work, Petitfort took it up and tried to come up with even better models. Now, as we go forward, we will actually not follow the chronological order. We will first look at the structure maps that were developed by Petitfort, and then after that, we will look at what Villars have been doing. So, the concept that Petitfort had was a fairly straightforward concept. He wanted to arrange all the elements along a scale that describe the chemical properties of the individual elements. Sounds familiar? That is pretty much like the periodic table. In case of David Petitfort's structure maps, he decided that Pauling's electronegativity was actually something which would be a good descriptor of the chemical properties of the elements. Now, Pauling's electronegativity is going to give you fractional values. So you will be having a bunch of decimals. So you could have an electronegativity, let's say, of 2.68 and so on. So back in the 1980s, when computers were not quite as powerful and computer storage was a problem, Petitfort didn't want to use that type of numbers for the purpose of storing the data for his computer code. And so he decided that instead, while he wanted to arrange all the elements according to Pauling's electronegativity, he also wanted to use a much simpler numbering system. And so that is where he went to one of the earlier attempts of the periodic table, which was taken by Mendeleev. So essentially, Petitfort decided to arrange the elements according to Pauling's electronegativity, and he found that this can be done if he used the Mendeleev number uh, in order to do that. So the Mendeleev number turned out to be a very convenient way in which he could handle the storage issues. So Petitfort went ahead and designed a 2D matrix. It was 2D because he was looking to predict the structure of binary compounds. And so that would have two different elements and they would have two different electronegativities. So when he designed this 2D matrix, he basically had two axes. One would be a chi-A axis, which is the electronegativity of the A elements, and then you have a chi-B axis corresponding to the electronegativity of the B elements. And then having done that, he started plotting different stoichiometric compounds in the chi-A, chi-B coordinate system for this AB compounds. So initially he started with AB compounds, which is a 1-to-1 stoichiometry. After that, he repeated the same for A2B, A3B, AB2, AB3, and so on. So this was actually a fairly laborious task, but it was unique in the sense that it was an attempt at classifying this crystal structures of binary compounds using some rather simple metrics. In this case, that was just the Pauling's electronegativity. So this was, in fact, a very interesting piece of work. And so what I've done, I have put up the references to the original papers by Petitfort. In case someone is interested, you can pause the video, you can take up these references and go deeper into them. Now, what is interesting is if you start ordering the elements on the y-axis, we have got chi, which is basically your Pauling's electronegativity. And then after that, what we do is we simply start going across the period and we start ordering the elements according to their electronegativities. So for example, if you look at this initial part, you've got beryllium and you've got magnesium fairly early in the period and then high up, relatively high up as far as the electronegativity is concerned. And when you look at these two compounds in the periodic table, these two elements in the periodic table, you will see that beryllium and magnesium are over here. Similarly, after that, what you find is you've got calcium right below magnesium, you've got calcium. After calcium, you have strontium and then barium. And again, you've got strontium and then barium. As you move further, you will see that there are certain changes. So again, you have scandium over here in the periodic table, and then below scandium, you've got yttrium. As you go even further, you will see that there is a slight change. So you've got titanium corresponding to the titanium over here. After that, you've got the hafnium. You've got hafnium over here, and then you have zirconium. You've got zirconium over here. So basically, as you keep on organizing these elements according to the electronegativity, while you go from left to right on that period, you see that you essentially start recreating the periodic table almost in the exact same order, but not quite. There is going to be a slight difference. So you have vanadium, you have tantalum, niobium. Here you have got vanadium, niobium, tantalum. Similarly, you have chrome, tungsten, moly. On the periodic table, you've got chrome, moly, tungsten, and so on. So you can actually start finding this type of trends in the periodic table, and you can start arranging the elements, and you almost end up replicating the periodic table. So having seen this, 24 now had the confidence that he could actually use this Pauling's electronegativity as a way of classifying, as a way of ordering these elements, and then based on where the elements appear in that order, the hypothesis was the structure of the compound can be predicted. So just to give you some idea, let me just show the arrangement of the elements themselves. So you start with helium, and helium, the Pauling electronegativity is 0, and then as you go down, the electronegativity is going to increase until you come all the way to the halogens, the oxygen and halogen, where the electronegativity is going to be very high. And all of these are then arranged according to the Mendeleev number. So if you look at this table, you have got the Mendeleev number over here, and then you have got the Pauling's electronegativity. Now, if you start looking at this table carefully enough, you will start seeing some rather interesting trends. So if you look at this first set of elements, you will actually find them to the extreme right of the periodic table. These are basically your inert gases. So helium, neon, argon, krypton, and so on. Then when you look at the next set of elements, you will find that these elements are found on the other extreme of the periodic table. Similarly, you can keep going forward. The next set is radium, barium, strontium, calcium, and if you look at it, you've got them right next to the first group in the periodic table. And then again, you have got yttrium and scandium. So you've got yttrium and scandium over here. And then what happens is, after scandium, as you go down, you go from yttrium to scandium, and then you get into the rare earths. So rare earths means starting from lutetium, erbium, dysprosium, and so on. And so this rare earth block is going to appear at the bottom of the periodic table. And similarly, you can keep going and you can keep creating the transition metal block as well. If you go further out towards the end of this table, you will get to the halogens. So astatine, iodine, bromine, chlorine, and so on. So you can keep on organizing, you can keep on going down this table uh, according to the Mendelev's number, and you can keep recreating this periodic table. So once Pettifor went ahead and ordered his elements in this manner, uh, he now started making 2D plots. So this is just like what we discussed. One axis is chi A, the Pauling's electronegativity for element A. The other axis is chi B. And then basically what he does is he takes the combination of different elements and he simply starts plotting them over here. All right. And then what he does is he repeats this process for different crystal structures. So let us say that this blue squares, they are corresponding to one type of crystal structure. The red circles are corresponding to a second type, and this green diamonds, they correspond to a third type. So the interesting part is if you look at how these points show up in this chi A, chi B 2D space, you will see that they are actually very well separated. So you can start drawing lines and you will see that you basically separate the space into different regions, and in each region you have got one specific type of crystal structure. Now of course the schematic that I am showing over here is rather simplified. The work that Pettifor did was much more complex than that in terms of the number of data points he dealt with. So for instance, for this AV compounds, he had a total of 574 points. And as you can see that these compounds line up very nicely in different regions of the 2D space. Some of the things you will see over here, just as an aside, you have those different points associated with different structure types. So what really is a structure type? Basically, anytime you discover a new crystal structure, you assign a structure type to it, and the name is given after the compound for which that structure was seen for the first time. So that's why you've got this NaCl as a structure type, you've got CSCl, zinc blende, copper titanium, and so on. So you've got a bunch of different structure types. And these are all for the AB compounds, meaning for the 1:1 stoichiometry. Similarly, he did the same exercise for AB2 compounds and AB3 compounds, and once again he could see that there are certain clusters in which this type of compounds are actually, and so that was rather interesting. But there is, of course, one challenge when you do the classification of crystal structures like this. So, in order to demarcate the space, Pettifor was drawing this type of lines, that on one side of the line you have one type of structure, on the other side of the line you have other type of structure, and so on and so forth. The problem here is you can draw the line only after you have done the experiment, only after you have actually observed what the crystal structure is. So in that sense, this approach is more of a classification type of approach. It's not really that much of a predictive approach. So that was one thing. Second thing, supposing you come up with a new compound and this compound has the structure type that you are looking at. It has the same type of crystal structure, but supposing it falls a little bit outside the lines within which this is supposed to occur, then the lines will have to be redrawn. So in that sense, this is just like machine learning, that any time you've got new data coming in, your entire machine learning approach is going to consider that data and the predictions starts changing slightly. So that type of update possibilities always exist with the Pettifor map. Now, David Pettifor was a physicist, so he was not just comfortable with only looking at this classification of crystal structures according to the Pauling's electronegativity. He wanted to find a physical basis why this idea of Pettifor map worked. So this Pauling's electronegativity is like a phenomenological parameter. The question that Pettifor asked is, why is this mapping based on this electronegativity going to be so effective? In other words, what is the origin of this well-separated structural domains in this chi A, chi B space? And to answer this question, Pettifor proposed something called a structural energy difference theorem. So we are not going to get too much into the math, simplifying the math quite a bit. what we do is we start with this very well-known expression that the overall potential energy is going to be a sum of a repulsive component and an attractive component. So U rep, that is the repulsion term, and then U bond, that is the bonding or the attraction term. Alright, so now according to the structural energy difference theorem, the difference in energies between any two crystal structures is given as delta U, which can be approximated as the difference in the bonding energies for those two structures. And this was having an underlying assumption, and the underlying assumption is when you are looking at the same pair of atoms, regardless of whatever structures you are looking at, the repulsion term comes when you are forcing the atoms one on the other. And so that is really not going to change too much regardless of whatever crystal structure you are looking at. The bonding term, the attraction term on the other hand, was going to change, because as your crystal structure changes, the equilibrium separation is changing. But there is a limit for a given pair of atoms as to how much you can push one on top of the other. And so that's why Pettifor made the assumption that this repulsive term is going to stay more or less the same regardless of the structure, and therefore the difference in energies is mainly due to this attractive or the bonding term. So that was basically his structural energy difference theorem. And then of course you calculate the total energy by summing over all the bonds that you've got in the structure. So the key point I want you to take away with you is that optimized interatomic interactions eventually give rise to the crystal structure. This is something that Pettifor realized, and his structural energy difference theorem was actually based on lines of this point as well. Now we talked about Pettifor's map, but then we said that before Pettifor, Villars came up with some structure diagrams as well. So the reason we started with Pettifor maps is because they are actually much more simpler than the Villars map. So having looked at the Pettifor maps, let us take a look at what Villars was trying to do. And for Villars, he was using 3 coordinates, which means that he was actually looking at a 3D volume instead of a 2D plane. So in case of Pettifor, all of the structure maps were plotted on a 2D plane, the chi-A, chi-B plane. In case of Villars, there were going to be 3 coordinates. The way he chose the coordinates was also significantly different from Pettifor. And this is again something because as we go forward and we start taking up case studies in machine learning, you will notice that there are different ways in which you can add in features. So one way is you simply take the weighted average. So you work directly with the numbers which are there for the elements. The other way is you start looking at how much of asymmetry is there or how much of difference is there. So Pettifor's approach was the first one, where he was using the numbers itself, basically your electronegativities, whereas in case of Villars, he was looking at the difference. And so here his first coordinate was this delta Rs plus Rp. So Rs and Rp, these are the radius of the S and the P shells when this AB compound is forming. And so what he said is this difference in the Rs plus Rp is basically given by this term, that you sum up the radius of the S and P orbitals for A, and then from that you subtract the sum of S and P orbitals for B, and so that gives you a delta Rs plus Rp term. Similar to Pettifor, he also included a electronegativity, but it was not the Pauling scale, it was a different scale, Bassanov electronegativity scale. But then instead of using simply the electronegativity, he actually looked at the difference in electronegativity. And this is because he was looking at only compound formation, all right? So the idea is if you have an element which is electropositive and you have another element which is electronegative, they're going to come together and form a strong bond. And so the difference in electronegativity was going to be a marker for compound formation, and that's why he started looking at the difference. And then the third thing that he took into account was this valence electron count, or VEC. And the origin for using something like the VEC comes from the work of Hume-Rothery, where he showed very clearly that the selection of different crystal structures can sometimes depend on the valence electron concentration of the material. And so these were his three coordinates: the delta S, delta Rs plus Rp, the delta chi, and then the valence electron count. Now, the challenge in using three different coordinates is you are looking at an entire volume. And so to do the visualization properly, Villars had to make number of 2D plots. And each of these plots is like one cut through the 3D space. So when you take a cut through the 3D space, you end up getting a plane, and that's basically what Villars was doing. So in order to visualize, he needed to have multiple 2D plots, and he was basically trying to observe these areas of overlap along different coordinates for the different types of crystal structures. So just like he created the structure diagrams for AB compounds, he also made structure diagrams for AB2 compounds. Now, as he was doing this, he was able to recognize a key drawback in the process. He found that not all calculated combinations or the theoretical predictions for all different compounds could be found, because there's a bunch of compounds which we don't even know for sure were going to exist. So here what he thought was, if you did not have this calculated combinations or theoretical predictions through this first principles type of calculation, he would use Miedema's semi-empirical model for calculating the formation enthalpy. Miedema's semi-empirical model is again something that we are going to take up as we move forward. When we talk about feature calculation, we'll talk about the calculation of thermodynamic features, and that's where the Miedema's model will come. But for now, let it suffice to say that Miedema's model is a semi-empirical model, and that is the type of model which is going to allow you to calculate the formation enthalpy. So his modified approach was to combine the elemental features along with the interaction energies. So here's an excerpt from Villars' paper, and if you look at what he writes in this highlighted region, he says that this diagram, together with Miedema's model, which predicts whether the heat of formation is positive or negative, provides a powerful tool for predicting the structure types of unknown AB2 phases with high accuracy. So this is where Villars was headed. So increasingly his concept behind the structure diagrams was becoming much more sophisticated, but as they were becoming much more sophisticated, they were also becoming much more complicated. Now, as we move forward, I would want to highlight some parallels that exist between structure maps and machine learning. So you would have already come across the lectures on different types of classification methods in the first part of this course. And as you look at the work that was done by Villars and Petitfort, you can see that the key idea here is these are early forms of classification methods. So you are plotting in 2D space, 2D plane or 3D space, and what you are trying to do is you are trying to find areas of that space or areas of that plane in which similar structure types exist. In other words, you are looking for this cluster of crystal structures which are very similar to each other. So in that sense, this is not very much different from this K-point clustering type of thing that you would have studied earlier in this particular course. Now, all of this work was done in 1980s when the computational powers were not much compared to what we have got today, and therefore there was a lot of missing links due to the lack of the computational powers. So essentially people were looking at rather simple features or just the value of the elemental feature itself, and they were not really doing too much of the calculated features. So this is the part that was missing. This is something that we can now add, given that the computational power that we have access to today is much more than what we had earlier. So while both Petitfort and Villars appreciated the role of the interatomic interactions, they were unable to capitalize on it simply because the computational power back then was not what it is today.